Hello everyone, today we're going to go over how to compute a gradient of linear regression, which is used a lot in introductory ML courses. So the basics of linear regression is the following. We have an input variable, x, and we have two different parameters that we can choose to try and kind of fit a line, and from there we can make our predictions. And often we will call our predictions y hat, for example. And we're going to say that y is going to be equal to some kind of w times our x plus b. And this is just kind of a fancy way of writing what we've kind of been more used to, for example, the mx plus b, where the w in this case just stands for our slope, and the b stands for our y-intercept. So just a regular linear line, and this is actually where we get our linear in linear regression. But why we're using W and B is to conform with the general ML terminology, where W stands for weights and B for the bias. And usually how we use linear regression, for example, is that we can draw this plot where the x-axis might symbolize the number of square feet in your house, and the y-axis is the cost of that house. And we might have some training examples in the sense that we have gone out on the housing market and measured some different houses and see what their market value is. And our goal here is then to try and fit some linear regression line that is as close to all of these data points as possible. And here comes kind of the challenge. How do I determine which line is better? I mean, how do I numerically represent that this line is a pretty bad line and this line is also a pretty bad line? But if I draw something in between, that is actually starting to become a pretty good estimation of this problem. And one way you can do it is by defining what we call this cost function. And a function, or this cost function, is to say, well, how badly is our model doing? Like, how far are we from the goal? So our target is to kind of minimize this cost function. We want to get as close to all these data points as possible. And one way we can define this is just to say, well, what is the distance from one of these data points to the line? So for example, here we can kind of draw this distance where for one of these data points, so for example, I might pick this point right here that is at some location xi and some location yi. And this is kind of our ground truth label, is that this point is at this yi, but at this xi, we can see that our line is going to give a different answer, kind of our prediction answer for this example. And to get the difference, or kind of the distance between them, we can say, well, what is the distance between our predicted value and the actual value? So, or yi in this case. But then you might say, okay, well, what happens if our predicted value is going to be less than the actual value? Then this expression is going to be negative. And if we want to minimize the cost function, then we just want to get as far as possible on this side. So to only get positive costs, we can take all of this and then make it squared. And if I just substitute back in what I had for y hat, so this expression here, we're going to get something like this. So wxi plus b, that was this thing right here, and then minus our actual label, or actual y, or in this case, our actual house cost. And right there, we have the cost function for one specific instance. But we don't want to just optimize for this point in particular. We want to try and find a line that is as close to all of the points. And that's why we also then introduce this summation. So we want to take and sum all of the costs. What happens when we take all of the distances? So we're going to start at the first data point. So that's going to be this data point here. And then we're just going to work our way through all our data points up until our xn. And then what we can do is to then take the mean of this. So we divide everything by n. And in this way, we have a general expression for our cost function. We go through all our training examples and we try and see how off we are. But the cost function is only good for the sense that we can just determine, well, if, for example, this line is better or worse than this other line. But how do we actually make differences? Like, how do we make a change to our line based on our cost function. And that's where the gradient comes in. So the gradient. And the gradient, so let's say I call this thing right here is going to be my C. And the gradient you kind of represent with this upside down triangle. And what I like to think of the gradient is kind of telling you how does it change? So if I change a little bit of my parameters, how will that change the final cost function? So what do I mean by that? Well, let's just say that you have one of these old radios and you want to kind of tune in the channel. In between the radio stations, there's gonna be a lot of noise, but you might be able to then tweak the radio and tweak the frequency you're at by just turning the knob. And just by trial and error, you can say, well, if I turn this knob a little bit this way and this knob a little bit that way, I'm going to get a better signal. It's going to be less noisy, or it's going to be a lower cost to that signal. And we just have as many knobs as we have parameters. So in this case, for this radio and this problem, our first knob is going to be the W knob, and the second knob is going to be our B knob. And it's much easier if we just treat them separately. First, I'll try and turn the W knob and kind of find the best things that I can do with the W knob. So I'll just turn it back and forth until I find the best sound that I can get just turning the W knob. And when I'm done with the W knob, I just go and only focus on the B knob, trying to turn that one to get as best of a sound as possible. And this just makes it easier than trying to turn both of them at the same time, because then you're not really sure like what knob is actually doing better or worse. So we're just turning them one at a time. And to say like how good or how bad we're doing when we're turning one at a time, that's what we call a partial derivative, using this little, I actually like to call it like a knob symbol. Think of like turning the knob. It has this little extra kind of motion instead of just a regular D. So think of turning the knob when we see the partial derivative. So we're saying, okay, what happens to the function, what happens to the cost function when we turn the W knob, and what happens to the cost function when we turn the B knob? So let's see what happens. So we're saying, for example, if we want the cost for a specific training example, for example, then we want to say and focus on what is taking kind of the partial derivative of all of this thing here. So that's going to say that, okay, we want to take, first of all, the partial derivative of our C function with respect to our W, and we also want to take the partial derivative with respect to our B. And now if we want to take the partial derivative, again, we have this business all of here, so all this stuff, and we can use U substitution to make this a bit easier. So, for example, I'm going to say, well, let U be all of this stuff in here. So W xi plus B minus yi. And then we want to say, well, what's the partial derivative? So the partial derivative of ci with respect to W, well, ci is just all of this squared. So it's going to be U squared because we have this squared here. And first of all, we can apply the chain rule. So we're going to say, well, it's all of this with respect to U times, we have, the partial derivative of U with respect to W. So that's going to be the first thing here. And how does this make sense? Well, we just want to get to a state where we just have the ci to the partial derivative of W. And if we're doing it this way, we can see that these two cancel out. And indeed, we get the partial derivative of U squared, which is C, with respect to the partial derivative of W. But let's do it one at a time. So what we get here is going to say, well, what's the partial derivative of U squared with respect to U? Well, we only have one knob to turn here, it's U, so this is going to be 2U. And then we're going to have times the partial derivative of U with respect to W. And if we look at here, we're saying, okay, just treat W as our variable for now. Let's just say that we're only allowed to turn this W knob, but treat everything else as a constant. We're not allowed to touch that. Those are not variables. Those are just some kind of numbers. So in this sense, if y is just a number, well, the derivative of y or just a number is just going to be 0. The derivative of some number is just going to be 0. And the derivative of w times some number is just going to be that number itself, right? So in this case, what we're only left with is this xi, because the derivative of w is going to be 1, and then we only have this constant left. And if we expand out, this is going to be 2xi, and then all things here. So wxi plus b minus yi, just substituting the u back in here. And if we want to do the b, so this is for the partial derivative with respect to w. But if we want to do the partial derivative with respect to b, it's going to be the same thing here. So it's going to be 2u. But now we're going to take multiplied by this with respect to b. So then I'm saying, well, now this thing is a constant. So this is just going to go to 0. Y is still 0. But now b is our variable. And when we take the derivative of just a lonely variable, that's just going to go and be 1 in this case. So here we're going to say 2u times 1, just like this. And if I expand this out, which is going to be 2wxi plus b minus yi. And now, if we just want to take the total gradient then across all our training samples, we can do the same thing. So I'm going to say, well, what's the cost function with respect to, for example, w? So I'm going to just do a little w here. And what that's going to be is going to have 1 over n, and then the sum of our 2xi wxi plus b minus yi. And what you'll often see is that people use for their cost function a 2n here, and that way we don't have to include our 2 in this expression. We can just do 2 just like this. And then lastly then, to make an update to our parameter, we can then say, well, let's just take this w and we'll update it. So it's going to be the old w minus some kind of alpha. So this is going to be our learning rate. So we're just saying, like, how big steps do we want to take using this information? So learning rate right here. And then times our derivative or our gradient for that variable. So for example, for our cost function with respect to w here. So if I'm going to be a bit more correct, I might say this is going to be then our partial derivative of our cost function with respect to our w. And this is going to be the learning rate. And why is it negative? Well, if we kind of think of having our cost function, it might look something like this. So let's say we're finding the slope of here. So we might say a slope of this. If the slope is positive, so pointing in this way, well, we want to minimize. So then we want to go the other way, right? So if the slope is positive, we want to go the other way. And if, for example, here, if the slope is negative, so if it was kind of this negative thing and it's pointing this way, well, again, we want to go the opposite way so that we're minimizing and trying to find this minimum. And with that, we've found the gradient of linear regression. I hope you learned something, and see you in the next one. Bye-bye.